So what we're doing actually is this lesson on exponential and logarithmic functions actually is covering, I don't know, 2 or 3 lessons that you would have had last year. It's all review, pretty much should be all review, but it's going to help us build the foundation for this unit. So let's take a look. There are really 3 different kinds of things we're going to be talking about. We're going to be talking about exponential functions, logarithmic functions, and we're going to talk about exponents also. So let's look at the difference. So an exponential function is a function that has a variable as an exponent, like 2 to the x. That's an exponential function. All right, we also deal with exponents, like x squared. This is not, although it has an exponent, it is not an exponential function. Exponential functions have a variable in the exponent, and others, like polynomials, have a variable as the base. So these are very different entities. Now we will be dealing with laws of exponents, which, apply, well, just in general to any exponent. So we'll look at that, and we'll look at logarithms. So an exponential function, we just talked about that, has a variable in the exponent. This is a general form of an exponential function. Just in general, what the general form would look like, where c is some number, a constant. A is some number, some base. Could be anything as long as it's bigger than 0. And x is the variable. That's just a general exponential form. We also have something kind of fun over here. It's the natural exponential function, basically the Euler number, E. This is the definition of the Euler number. It's kind of fun, isn't it? I mean, an Euler number, it has a limit definition. That's fantastic. So now that we know some about limits, let's kind of look and see what this is saying. As n gets increasingly larger, we know what would happen to this fraction, right? This fraction, as n gets increasingly larger, this fraction tends to 0. And so we basically would have 1 to infinity. And 1 to infinity is not 1. Isn't that crazy? It's kind of mind-blowing. 1 to infinity is not 1. It's the Euler number or something else. It's not necessarily 1. That's an indeterminate form that we'll talk about next year. But that's kind of fun. That's a definition of the Euler number. So now let's get to our laws. These exponent laws can serve to drive a student crazy. If you do not have these in your brain, like memorized in your brain, you will make mistakes all over the place, and it will cause all kinds of problems. So this is a review. I'm going to remind you about the exponent rules that we still are breaking from time to time in here. So let's make sure we don't break these rules. Let's look at them. So when I have the common base and I am multiplying them together, I add their exponents. That's what we do. That's a rule. So these things need to be like embedded in your memory, like 1 plus 1. I mean, they need to be in your memory. So that's what happens when we multiply common bases. When we divide common bases, we subtract the exponents. That's just the rule. Okay? When we have a product raised to a power, I can distribute the exponent inside there. That's okay. It is not okay if it's a sum or difference raised to a power. We get into all kind of trouble with that. This cool little rule only works if it's a product or a quotient. See how that is? A product raised to an exponent, we distribute the exponent. A quotient raised to the exponent, we distribute the exponent. Not, let's say, a plus b raised to the x. That is a no-no. We do not distribute the x to there. Okay? Some of us kind of take liberty with this rule and kind of try to apply it to everything. It only works if it's a pure product or a pure quotient. That's it. Okay, no addition or subtraction in there. Then we have this rule. This is the rule that tells us how to switch back and forth between exponential form and logarithmic form, or excuse me, exponential form and radical form. Go back and forth. We see the base of this denominator is the type of root that we have, and the numerator of this exponent is what we would raise the inside to. That's just how we go back and forth. That should be a review. So b to the 0, anything to the 0 is 1. I mean, except for 0. 0 to the 0 is an indeterminate form, which we will talk about next year, if you're in BC Calculus. All right, so here is a rule. We probably remember this from last year. If we can get the bases the same, then it's like we ignore them. They don't go away. We just ignore them, and we set the exponents equal to each other. So that's a rule. We can do that. Number 7 is a less used rule, but it's still a rule. It kind of is looking at the other situation. What if our exponents are the same and our bases are different? Well, if our exponents are the same, we are allowed to set the bases equal to each other. So we don't use that one as much, but it's still a valid rule. Let's move over here. So when we have power to power, remember that's multiplying. And then if we have a negative exponent, we can rewrite it by putting 1 over a to the positive x. So that's just a review. Hopefully those aren't any surprises for us. So those are our laws of exponents. So now let's look and remind ourselves, how do we go back and forth between an exponent and a logarithm, and an exponent and logarithm? How do we do that? This little box right here shows us the rules for doing that. All right, so let's take a look at this first one. If I have log base b of x is y, okay, to transform that into an exponential, I would take the base of the logarithm. That would be the base of the exponential, right? The base of the logarithm is the base of the exponential. Some teachers do this kind of thing, this little curly, loopy thing. I don't know, you can do that if you want. Basically, it's the base to the answer equals the argument. B to y equals x. That's how we would go back and forth between a logarithm and an exponential. So to go from an exponential to a logarithm, we know the base of the exponential is the base of the exponent. So log base b of x equals y. We're always traveling across, to the answer and then going to the argument. All right, so let's take a look at a couple more things. So we have this, just like we know the coefficient of this x is a 1, it's an implied 1. It's not there. And like the exponent to this is 1, we just don't write it, right? It's implied. Well, logarithms have a similar kind of thing. If you just see the word log, then the implied base is a 10. You probably remember that from last year, is implied base 10. So that's just an implied base. So here is converting this logarithm to an exponential. So 10 to the y equals x, or log base 10 to the x equals y. Now let's look at the last one, our natural log, base e. We know if the log is base e, it's natural log. Natural log's implied base is an e. There's an e sitting right there, although we don't see it. Right, so to convert that, it would be e to the y equals x. Okay, so just a reminder, we should have dealt with this last year. So let's look at this last little box, see what's going on here. Properties of logarithms. So these properties help us simplify things. They're just very helpful. So if I have log base a, any base, could be 2, 3, 5, 20, any base, of 1 is 0. So let's talk about that. If I converted this to an exponential, that would make sense to you. A to the 0 equals 1, right? Anything to the 0 is 1. So this hopefully makes sense. Here, if my base of my log matches the argument of my log, then that result is 1, which also makes sense. A to the first would be a. We convert to an exponential. This one, I have a to the log base a of x. So if I have an exponent to a log with the same base, right? So I have a to the log base a, then my answer is x. Just another way to simplify. And then over here, these properties of natural logs. These are kind of important. Actually, we use those in calculus. We need to know that natural log of 1 is 0. That's just something that you have to memorize. We have to know that natural log of e is 1. We have to do those kinds of things without a calculator in calculus, and so we're beginning to learn them probably last year and into this year. We have to know that. We have natural log of e to the x. The natural log is a base e. That cancels on left with an x. Just likewise, I have e to the natural log of base e of x is x. Now these kinds of rules are pretty important. Sometimes we have a hard time remembering them, so I'll show you a way around it if you have a hard time remembering it. We have some examples where we use those rules, and I'll kind of work with you on that to work around that. Let's remind ourselves one more thing about logarithms, pretty important, and that is this base can't be negative, and it can't be 0. And this thing right here is called the argument. Just like, remember how sine, cosine, the trig functions have something called an argument? So does the logarithm. This argument can't be negative and it can't be 0. If it is, then it's an imaginary logarithm, and we really, I know, don't be disappointed, we really don't deal with imaginary logarithms in here. I know it would be fun, but we just don't. So just know that you can't, for our purposes, we're not doing that. We're not having a negative or 0 base or argument for a logarithm. Okay, that would be imaginary, and we're not going there. All right, so that's a lot of rules. You probably covered this in like, I don't know, 3 or 4 lessons last year. Are we okay with that? Let's move on. Let's do some examples. Okay, so let's look at graphing. And so we have an exponential to graph, and I like graphing using transformations. You don't have to. You can graph however you like, but my preference is to use a transformation. So what I would do is I would graph the parent, and I always use -1, 0, 1. That is sufficient to get whatever graph you need, -1, 0, 1. So 2 to the -1 is 1/2, 2 to the 0 is 1, and 2 to the 1 is 2. So those are my parent points. And then I would simply transform. I just do whatever is going on here, I just transform the points. So these are my transformed points. Alright, so let's see what's going on. I really just have a y transformation, don't I? I don't have an x. If I had an x transformation, it would be up here with the x. It would be a little bitty up here. But I just have a y transformation. It's basically taking all the y's and subtracting 3. So I'm going to copy down my x values. Those aren't going to change. And I'm going to take all my y values and I'm going to subtract 3 from them. So 1/2 minus 3 is what? -2.5. 1 minus 3 is -2. And 2 minus 3 is -1. So let's plot those points. So I go -1, -2.5. I go 0, -2, and 1, -1. So let's remind ourselves what exponential graphs look like. If you remember from last year, remember they kind of float along an asymptote and then they jump up. Remember that? So there is an asymptote that we would have to graph. It is actually right here. Let's talk about this asymptote. You should be able to tell from your points where it is, but let's say you don't. You can actually tell from the equation itself. All exponentials have at least one horizontal asymptote. All the regular ones, the ones we're going to be dealing with, have one. Okay, and so what would move the parent's asymptote is at the x-axis. The only thing that would move the asymptote is a y shift. The only thing that would move one of these guys, the exponential's asymptote, is a y up or down shift. Nothing else would move it. This has a y downshift of 3, therefore my asymptote shifted down 3. Okay? Think about it. If I had a, let's say I had an x shift and I moved left or right, that's not going to change the location of the asymptote, right? Or if I had a, let's say, it multiplied, a 3 multiplier and made it bigger, it's not going to change the asymptote. The only thing that's going to change the asymptote is a up or down y shift. And this one did. So we are going to write the equations of the asymptotes, and we're going to do domain and range. So the equation of this asymptote would be what y equals -3. My domain is negative infinity to infinity, and my range is negative 3 to infinity. Okay, we okay with that first graph? Okay. Let's take a look at a graph of a log. We're going to do a natural log this time. So I would, do the parent, ln x. Really graphing natural logs, or any log kind of logs, really not convenient to leave it in that form if you recall. We don't have those numbers memorized. Way easier to transform it into an exponential. So we would be working with e to the y equals x. This is the exponential that we're going to be working with. We're going to get our numbers off of here. And I just transform this. I set this equal to y, and I transform to get that. Right? E to the y equals x. So this time I'm going to put my negative 1, 0, 1. I'm not going to put it for x. I'm going to put it for y. Because that's what's convenient. It really would not be convenient to put it for x. And I have to figure out what exponent produced that. That's really not, that would be hard. Why would I do that? I'm just going to put negative 1, 0, 1 for my y. And e is 2.7, blah, 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 2.71828. We're just going to use 2.7. Just use 2.7. That's plenty enough for graphing. We don't need to get any more accurate than that. So if we do 2.7 to the negative 1 power, it'd be 1 over 2.7. Right? That's what it would be. And 1 over 2.7 is right around a third. A little bit more than a third, but right around a third. So 2.7 to the 0 power is 1. And 2.7 to the first power is 2.7. Those are my parent points. Okay? So now let's look at the transformed points. Let's see what's going on here. I have an x transformation here. And those x transformations, they're just trouble, aren't they? It's always opposite. It says minus 2, but the transformation is actually right 2, right? It's plus 2. So I'm going to have to take, I'm transforming my points. Right? I'm not plugging in points. I'm transforming my points. I'm going to have to take all of my x's, and I'm going to have to add 2 to them. Right? That's what the transformation tells me to do. So all of my x's I add 2. So 2 plus 1 over 2.7 is 2, and 1 over 2.7. We do 2 plus 1 is 3. 2 plus 2.7 is 4.7, and my y's stay the same. Now let's talk about this asymptote. Remember, all natural logs have an asymptote, a vertical asymptote. All logs have a vertical asymptote. The parent one is at the y-axis. So what transformation do you think is going to move my asymptote for a log? It's the left-right, right? And I have a right 2. So my asymptote should be right here. Now we're going to graph the points and make sure, but I should be able to read it off of the equation. I shouldn't have to just graph points to know. So let's graph our points. So we have, 2 and a little bit bigger than 1/3, so 2, and then negative 1. Then we have 3. Let's see. We have 3. Oops, because I'm goofy. Okay. Okay, so we have 2 and a little bit bigger, and negative 1 is right here. And then we have 3, 0. And then we have 4.7, 1, 2, 3, 4.7, so 4.7 and 1, like right there. So there's our logarithm. Our asymptote is x equals 2. Our domain would be from 2 to infinity, and our range would be negative infinity to infinity. Okay, there's a quick reminder about graphing exponentials and logarithms. Are we okay with that? Okay. All right, let's move to exponents, exponent rules. Okay, so I'm going to tell you what I do every single time. You can do it however you want to, but I'm boring. I do the same thing every single time because that just helps me not make mistakes. When I have parentheses, the very first thing I want to do is try to get rid of them. That's just what I like to do. So I have an actual, just a quotient here, multiplication. You know, I have free range on all my exponent rules. So I'm actually going to distribute. I'm going to use the exponent rule from the other page and distribute. So that would give me b to the negative 4 over a to the negative 2 times, and then a to the negative 6 over b to the negative 3. That's the very first thing I do, is get rid of parentheses. The second thing that I do is to get rid of negative exponents. It's just the order that I do things in. So I'm going to change all the negative exponents to positive exponents. So, and I'm going to group them together because this is by multiplication. So that b is going to go in the denominator, b to the 4th, a squared in the numerator. Well, let's work on this one. A to the 6th in the denominator, b cubed in the numerator. Okay, so that's step 2. Step 3 is getting the bases together using those other rules. So I have 2 a's on top and 6 a's on the bottom. How many a's am I going to be left with? 4, and where are they going to be? On the bottom, in the denominator. So I have a to the 4th down here. All right, let's work on the b's. I have 3 b's in the numerator and 4 b's in the denominator. How many b's am I going to have left? 1, and it will be in the denominator. And so I don't have anything left up there, so that means it's a 1. So there's my simplification. Okay? Number B. I don't like parentheses. I would want to get rid of them first, but I can't. I am stopped from doing that. Why? Because of the addition sign. I cannot distribute this negative 1 throughout here. That is a huge no-no. Cannot do. Okay? So, I can't do my first priority. My first priority is parentheses. Can't do that. I'm going to move to my second priority. My second priority is negative exponents. So I'm going to get rid of this negative exponent right away and do 1 over a negative 2 plus b negative 2. And that's to the first power. When I move this down, it doesn't change their exponents. It's only changing this one. I still have negative exponents to deal with. So I would continue on getting rid of negative exponents. That's just what I would do. So I have, that turns into 1 over a squared plus 1 over b squared. Now I have a complex fraction. I do what I always do when I have complex fractions. I find a common denominator, add them together, flip and fix the fraction. Same thing every time. Find a common denominator. So the common denominator would be a squared, b squared. So this fraction would need a b squared. This fraction would need an a squared. Okay, I've found a common denominator, add them together. Now I flip and fix the fraction, the complex fraction. We've been doing this kind of thing, or this concept, since elementary school, right? When we divide fractions, instead of dividing this 1 divided by this fraction, instead of dividing, we multiply, right? 1 times the reciprocal of this fraction. So my answer is going to be a squared b squared over a squared plus b squared, or b squared plus a squared, doesn't matter. Okay? How are we with that? Number C, or letter C. Don't have any parentheses to deal with, so I'm going to work on my negative fractions, or excuse me, my negative exponents. And I can't tell you how many students would take this and move it to the denominator. Why are we not allowed to do that? Why can I not move this to the denominator right now? Yeah, it's being added. It's being added. It's not a thing. It's not a thing that we do. Okay? These rules will really help you if they're in your brain, and if they're not in your brain, you're going to get really hurt. So we need to have them in our brain. So no, I can't move that down. But I'm going to leave them where they are, and I'm going to turn them into positive exponents. That's what I'm going to do. So I have x to the 5th plus 1 over x squared over 1 over x cubed. Okay, so I got rid of my negative exponents. Now I'm going to fix my complex fraction. Let's think about that. What I would do is I would take this, 1 over x cubed, flip it upside down, right, and distribute to the numerator. That's what I would do. So I would get x cubed times x to the 5th plus 1 over x squared. Okay? Now I distribute, and I get x to the 8th plus x. How are we with that? Okay? Okay, last one. Got all kinds of things going on there. In the form that it's in, there's absolutely nothing that I can do. Absolutely nothing. So that means, of course, I'm not going to give you a problem where there's nothing to do. That wouldn't make any sense, right? So there's something to do. Let's think. Back to last year. What about making our bases the same? If our bases are the same, we can do a lot of work there. I also have a mixture. I have exponential form underneath, and I have radical form over here. I really don't want that mix. I'm going to go all exponential. Okay, so I'm going to take these, and let's see. 5 looks like a good base. 25 is 5 squared, right? And 125 is 5 cubed, so it looks like we need to turn everything into a base 5. So I'm going to move up here. I'm going to make that to the 1/3, so I'm using exponential form. So 125 is, what, 5 cubed times, then we have 5 to the 4n over 25 is, what, 5 squared, so 5 to the negative 2n, and that's all raised to the 1/3 power. Okay, so let's deal with negative exponents now. I could distribute the 1/3 right now, but it would give me a little bit of a mess. I want to wait. I normally would. I would normally want to get rid of the parentheses right now. I would want to distribute the 1/3, but then I get a bunch of fractions, so I just want to kind of pause and see if there's anything I can do to make it a little bit simpler inside before I do that. I'm going to take this negative exponent, move it to the top, so that gives me 5 to the 3n times 5 to the 4n times 5 to the 2n, all raised to the 1/3. Okay, so they're all common bases. When we're multiplying common bases, we add the exponents. So 3n plus 4n is 7n, 7n plus 2n is 9n. So I have 5 to the 9n raised to the 1/3. So now I do power to power. Right, and 9 times 1/3 is 3. So the answer to part D is 5 to the 3n. That big mess of a thing turns out to be 5 to the 3n. Okay, how are we? All right, the last examples we're going to evaluate. So let's take a look at that. Now, what I like to do when I'm faced with a problem like A is I like to set it equal to a variable. I mean, any variable is fine. Do you have to do it this way? No, you don't have to do it this way. It's what I like to do. So I'm just going to set it equal to x, and then I'm going to turn it into an exponential. So 7 to the x equals 1 over 343. Okay? Now, you're not going to get anything typically that's impossible to solve. So 343 must be 7 to some power, right? Without a calculator. I mean, with a calculator, I could give you crazy stuff, but without a calculator, I mean, 343. So 7 times 7 we know is 49. 49 times 7. That's 3 cubed, isn't it? I mean, excuse me, 7 cubed. So really, it's 1 over 7 cubed. So that would be 7 to the negative 3. Right, so 7 to the x equals 7 to the negative 3. My bases are the same. So since my bases are the same, I can ignore them, and x is negative 3. Well, my answer is x. So my answer is negative 3. Now, I introduced the variable x. You don't really need to write it in your answer. I mean, you can if you want to. I'll be okay with that. But we introduced the variable x. They just want to know what this is equivalent to, and it's the same as negative 3. Are we okay with that? Okay, so let's take this one. Let's convert it. So 4 to the 1.5 equals x. You're thinking, oh, that was too easy. Yeah, it kind of was. We know there's probably more to it than just that. Hopefully we know that I wouldn't give you something that easy, right? That'd be boring. Okay, 1.5 is, let's put it as a fraction. Is that 3 halves? So 4 to the 3 halves equals x. All right, so let's think about what this fraction is. This denominator is the type of root, and the numerator is the power. Now, I'm not good with big numbers in my head. I always do the root first because that makes the number smaller. Do you have to? No. I mean, you could do the exponent first, but I don't really want to do 4 cubed and then square root that. I really don't want to really do that. I want to square root 4, which is 2, and then I want to cube 2. 2 times 2 is 4, 4 times 2 is 8. So this is 8. Okay, we okay with that? Okay. This last one is a rule from the other page. If you know the rule, you can tell me what the answer is. If you don't know the rule, then it looks like a big mess. Okay, if you know the rule, you would tell me the answer is 2x. If you don't know the rule, let me show you what you could do. So what I would do if I didn't know the rule is I would set it equal to some variable, not x, something else, like y. Then I'm going to convert it. I'm going to convert it, it's base e, it's an exponent. I'm going to put it into a logarithm. So base e has, which logarithm matches base e? ln, right? So I would do ln of y equals the exponent, ln of 2x. When our logarithms are the same base, what can we do to the arguments? Set them equal to each other. So y is 2x. Now I made up y. Y is the answer. The answer is 2x, which I could just read from that if I knew the rule. If I don't remember the rule, then I can get to it this way, by setting it equal to a different variable and then transforming it. Okay, we okay with that? Okay.